Okay, so meanwhile I can start with the notice. I have to publish notice. Should so hi, good evening. Hi Priyanka, good evening. So how are you? So guys, is my screen visible to everyone there? Is my screen visible to everyone? So how are you all? Hi Priyanka. Hey Gidra. Okay, so we are in YouTube live right now. So hi guys, hi, good evening everyone. So good evening Chinmay, good evening everyone. Hi. So hope everyone is doing great. How was your festival celebration? So yes, so cool. So anyone burst the crackers and all? I mean, did you guys try to burst the crackers? Yes. Achha, I didn't do. Okay, guys. So in today's class, we'll be discussing about the last part of applications of Gauss law. That is for the application of Gauss law for the calculation of electric field due to, calculation of electric field for an infinite long plane, right? So we were pending with that. So we'll have a quick revision on whatever we had completed so far. So that is, we'll just have a glance on application of Gauss law on spherical conductors, then the infinite conductor, then we'll come with the actual discussion on application of Gauss law for plane surface. Okay, infinite plane surface. Then we'll start with the revision stuff. Then once we are done with summary and revision of entire chapter once, we can start with our next chapter, that is capacitance. Okay, so I'm quickly launching a technical poll, guys. Please take the technical poll if I'm visible. I mean, if the voice is clearly audible and the blackboard is visible clearly. Please take the poll, guys. That chapter once, then we can start. So, say no to crackers. Say less. Nice, Hari Prasad. Cool. Yes. Guys, please give me the give me the technical poll. Please take your technical poll. Let me know if my voice is audible and the blackboard is visible to everyone. So also please invite your friends to the class. So cool. Thank you, guys. Acha, Krishmodi, cool. Is it the new year? I don't know if it's the new year. Okay, guys, come on. Let's start with the class. Then I'm going to end the poll for you guys. Thank you. Thanks for the voting. So, guys, in applications of Gauss law, we started with the solid sphere. So we'll have a quick revision of what we had learned in our previous class. So we had a solid sphere of radius r, say in this case, charge sphere. What, sir? So guys, tell me what was acting as a outer cover in this case. So for Gauss law, for application of Gauss law, we required two things. What were the two things we required? For Gauss law, what were the things we required to apply Gauss law? So we required and enclosed or cover, right? We require, say, can we call it a cover, or can we call it a surface in which my charge is being enclosed. So if I want to say, if I want to apply Gauss's law, what is the expression for Gauss law, guys? What is the expression for Gauss law? What do we calculate using Gauss law? Please reply in chat, everyone, YouTubers and JPMC guys, please reply. So why do we require Gauss law? What we calculate in Gauss law? So what did we calculate in Gauss law? Guys, yes, I request everyone to be active and please respond. So Gauss law ಏನಕ್ಕೆ ಬೇಕು? Why should we require Gauss law? What was the thing which we calculated using Gauss law? Yes, Gauss law's application was to find electric field, but what was the actual Gauss law expression? What was the actual Gauss law's expression? Yes. Yes, correct Priyanka, correct Krishna Modi, correct Ramakrishna Reddy. Guys here at Zoom, please respond. So we were calculating the electric flux, right? We are calculating the electric flux. Electric flux phi E is nothing but closed integral of E dot dr or E dot dA, right? So if we try to calculate this, we get, okay, we ended with a common formula. What is that common formula? It is nothing but Q enclosed upon the epsilon naught, or epsilon, to be general, it's epsilon. So this was, so we eliminated this and gave only this. So my electric flux depends only on the charge enclosed inside a closed surface, and also depends upon only the material medium. We had seen this. Now, yeah, we had applied Gauss's law for spherical conductor. To find Gauss's law here, the equipotential surfaces created by the spherical conductors were acting like the enclosed surface or Gaussian surface, right? Guys, please click on yes if you remember. So these equipotential surfaces were acting as Gaussian surfaces. You remember this? So, yep, cool. Then these, one of these equipotential surfaces were considered to calculate the electric flux, right? So we applied for the electric flux in case of say outside the sphere. Say in the case of outside the sphere, what was the flux? So we got that in the case of this case, we got the flux to be similar to that of a point charge. E is equals to Q by 4 pi epsilon naught R square. So for the electric field of a solid sphere outside the sphere at a radius or at a distance r, we got the expression similar to that of what? So it was similar to that of a point charge, right? Electric field due to a point charge. Then, yeah, again, in terms, we try to calculate the electric field in terms of surface charge density, that is rho. So if rho was given as v times, or q was given as v times of rho, where v is 4 by 3 pi r cube, the volume of this solid sphere, then electric field was given as rho r cube by 3 epsilon naught r square in the direction of r cap. So this we had studied in our previous class. Again, then when we try to calculate the electric field inside the sphere, we got another same result, similar result, where it was E is equals to integral E is equals to rho r times of 3 epsilon naught, rho r by 3 epsilon naught in the direction of r cap direction. So we got electric field as rho r by 3 epsilon naught. So this was in the case of electric field inside the solid sphere, right? So this we had seen in our earlier classes. Next, we had tried to find the electric field due to an infinite long charge. So guys, even here, what was my Gaussian surface? Please reply. Even in this case, what was my Gaussian surface, everyone? What was my Gaussian surface here? I'm waiting for one reply at least. Please, guys, come on, reply. So ಇದರಲ್ಲಿ infinite long charge ನಲ್ಲಿ Gaussian surface ಯಾವುದು? What was my Gaussian surface? So it's again the equipotential surface, right? So there were, yes, correct, Prajwal. So again, the equipotential surfaces created by the infinite charge, these were nothing but the cylinders, concentric cylinders, right? These acts as a Gaussian surface. So we considered a rod of length L, and whose surface charge density was given, linear charge density was given as lambda. Saying out of these, if it had electric field emerging out, then we had the equipotential surface of length L. Let us consider the equipotential surface of length L, whose radius or whose distance from the center of the uniformly charged wire is R. Then if so, we consider three fluxes here. In this case, it had three flux, phi1, phi2, and phi3, where phi2 and phi3 were the plane surfaces and phi1 was the curved surface. So then we had the flux given as, so electric field was emerging out, so only flux was due to the only flux which is considered was only because of the curved surface, right? Then the flux was given using the area vector and direction as phi is equal to integral E dot dA. So on simplifying, we get the expression as the electric flux is equals to ER is equals to lambda L by 2 pi RL epsilon naught. That is, on simplifying, we get ER is equals to lambda by 2 pi epsilon naught R. So this was the expression for electric field we got for an infinite long conductor. So guys, I think we tried to answer this question. I want you guys to answer this again. Please check if you have, if you remember this. So let's start with this. So once we are done with this, we'll start with electric field due to infinitely large plane. Okay, infinite plane. Please try to answer this, guys. So let me know if you guys still remember what we had studied so far. So yes. So YouTubers also please try to respond in your chat box. If you guys remember why, and we had discussed this question in the end, but it was there was no proper explanation given, right? I think so. I thought of discussing this question again. Yes, correct, Manju. Correct, Prajwal. Correct, Rakesh. Yes, correct, guys. So others, please try to respond in your polls. Yes. So the question goes like this: a Gaussian surface S1 passes through 2 point charges. So I'm trying to redraw. So there was 1 point charge Q1 and other point charge Q2. Between these, there was a Gaussian surface. So I'll try to take a Gaussian surface. Yes. So I had a Gaussian surface. It's a closed surface whose area is A. Okay, it's a closed surface. Now, this a Gaussian? Is this Gaussian surface possible? Is my first question. And we have one more, say, infinitely charged conductor, right? So between this, we had a Gaussian surface. I mean, we considered a surface 2 called as yeah, we had a surface like this which passes through this. Okay. Okay, I can draw like this. Yes. Now, which of these was the Gaussian surface? This was the question asked. So yes, correct. Ramakrishna Reddy, Divikarani, Bhargav, correct. And here Manju, Prajwal, Rakesh, correct. So there are others who have responded. Thank you. So guys, most of you have responded. So others who have not attended the class, please listen. So correct answer was option B, right? So why was it option B? So Gaussian surface can pass through a continuous charge distribution, but it cannot pass through point charges. That's the explanation which they give. So why not? It's because a Gaussian surface passes through a point charge, it cannot be judged whether point charge is enclosed or not. Say in this case, even if I consider a Gaussian surface here, say if I consider one complete Gaussian surface, but I can't exactly identify, or I can't exactly say whether this point charge is enclosed inside this surface or not. But when it passes through a uniformly charged conductor, then I can for sure I can say that this surface S2 is a Gaussian surface because there is some charge Q is equals to lambda times of dl, say, or I can say dq is equals to lambda times of dl, is being enclosed inside this surface. So this surface is possible, whereas this is not possible. Okay, this was what we had learned in our previous class. So yes, in today's class, we'll start with the application of Gauss law for to calculate the electric field for the plane surface. Okay, okay, guys, come on. Let's start now. So let us consider. So what happens in case of plane surfaces? Say in case of plane surfaces, how many sides do we have in a plane surface? Yes, cool. So how many sides do we have in a plane surface? So if we have a plane sheet, how many sides do we have in a plane sheet? Come on, guys. Yes, Prajwal. Prajwal, you raised your hand. Acha. Anusha, how? So we have two sides, right? So say I have a very thin plane sheet. Say if you take an A4 sheet, how many sides do you have? How many pages? Or in a sheet, how many pages? This is first page. If you try to turn over, you'll get the second page, right? So yeah, now if we consider electric field passing through these surfaces, say if I call this is my E1. Yes, correct, Bhargav, correct, Priyanka and Dimpan. Cool. So if I consider my electric field in this first surface as E1, and if I have the second surface on the second side, on the other side, inverted side, and if I call this as E2, then how can I draw? So what can I consider my equipotential surfaces as? Guys, come on, tell me. In case of infinitely charged plane, electric field is in both directions. Now, where can I consider my equipotential surface? Yes, correct. Where can I consider my equipotential surface? Yes. So this creates an equipotential surface which are parallel, right? Now, guys, tell me what is my flux? If you remember, what is flux? What is flux? Sir, why are you asking this question now? We know that. Then tell me now, what is flux? Flux andre ಏನು ಹೇಳಿ? Guys, everyone, please tell me what is flux? So flux is nothing but, yes, E dot A. Number of electric field lines passing through a given area. So these both are vectors. Anusha, that is magnetic flux. Here we are talking about electric flux. Okay. So, okay, I'll write phi E. Phi E is equals to E dot A, or phi E is equals to EA cos theta. Right. Now, if you remember the basics again, I don't know how much you guys remember. So, guys, yeah, for a plane surface, what are the factors which depend? I mean, what are the factors the flux depends on? Yes, correct, Ramakrishnan. Correct, Rebecca. Correct, Priyanka. So what are the factors which my plane surface depends on? If you remember, we had discussed this in our previous initial discussion of Gaussian surfaces or flux. So my factors which my flux depends on are: one, area; two, guys, come on, you guys tell me, please. Come on, tell me. Area of my plane sheet. Second thing which it depends on is angle, guys. So I think I told you this is my alpha. And for this surface area, what would be the angle, guys? Where would be the angle? For this given surface area, where would be the angle? Where can I write my angle? Towards the normal, right? Yes, correct, Marco. Cool. So it's towards the normal. So there is an angle alpha and there is an angle theta, right? There is an angle alpha and there is an angle theta. Now this angle theta for equipotential surface is 0 degree, but my alpha is 90 degree. Guys, you remember? More the alpha, more will be the number of electric field lines, more will be the flux. Less the theta, more will be the flux. I hope you remember this. So we can consider one such equipotential surface as my closed surface. Now, if you want to apply Gauss's law, first we have to consider to find electric field due to by applying Gauss law. So we need to check the two conditions. What were the two conditions, guys? If you remember, first thing is electric field. Electric field must be parallel to the area vector. Guys, hope you remember this. The first condition, I should consider my area vector dA. Should consider my area vector dA such that say if I consider a small area vector dA, what should it satisfy? What is the condition it should satisfy? It should satisfy two conditions. Where should I consider my area vector dA? So first condition is electric field passing through must be parallel to this area vector, and uniform electric field must pass through this area. Okay, this was the first condition which we learned. Say how to consider the area vector. For considering area vector, the first thing is when we consider that area vector, my electric field should be uniform throughout that area vector and it should be parallel. So we consider it in a symmetry such that it should be parallel. Okay, so should be parallel. Why should it be parallel? It should be parallel because my area vector and the direction of electric field both should be parallel because my theta should be 0 degree. This way I'll get my flux as maximum, right? Okay, so in order to apply Gauss's law to this condition for the infinite large plane, what we have to consider, let us consider cylindrical surfaces of length d. Say I have two cylindrical surfaces. Say I have one cylindrical surface of length d and cross-sectional area a. So let us consider a plane surface. Say this is a plane infinite long conductor. Okay, this is an infinitely long conductor. Okay, it's infinitely large in all directions. Now, in order to apply Gauss's law, I have considered a small surface. Say I have to consider the equipotential surface. So I'll consider a cylindrical surface, okay, of length d. So we had already calculated the electric field due to cylindrical surface. So it makes our calculation simpler. Now the cross-sectional area of this cylindrical surface is A. Similarly, I'll consider another cylindrical surface of cross-sectional area A and length D to maintain the symmetry, right? To maintain the symmetry, I'll consider another uh, cylindrical surface behind this sheet. So on the other side of the sheet. So this is my first side and that should be my second side. Okay. Now, what I'll consider? I'll consider the the surface charge density, right? The surface charge density sigma to be, okay, the surface charge density B sigma. So why have we inserted cylinder? So we have not inserted the cylinder, Hari Prasad. So what we have considered is we have considered another equipotential surface. Say there was one more cylindrical surface of this thickness D. Now instead of taking this entire square or entire rectangular surface, what we took only a part of it. Okay, we cut only a part of it. Why? We this makes our maths life simple. Okay, so we have already calculated the electric field due to a cylinder, right, in our previous case, Hari Prasad. So we had already calculated the electric field due to an infinitely long conductor due to a cylinder, right? In that case, we had already calculated. So from there, we know. Now, in order to apply Gauss law to this, to find electric field in the infinite plane case, so we are considering this equipotential surface as a cylinder on both sides. This makes us makes our math simple. Okay, so we have maintained the symmetry, and my electric field will be always parallel to this. Okay, my electric field will be always parallel to this, and we'll consider the surface charge density. We'll consider the surface charge density as sigma. Okay. So what was sigma, guys? Come on, tell me. Someone, please reply. What is the value of sigma? What is sigma actually? Surface charge density, sigma. In general, general expression for sigma, guys. Let me know if you are well aware of this. Sigma equals to, yes, q by a. Correct, Prajwal. It's q by a. Okay, what happens in case of this plane? Okay, let me ask one more question. So I have a plane, infinite large plane. So what would be the value of sigma on only one side? What would be the value of sigma on only one side? Okay, Madhavi, right? Ramakrishna Reddy, right? That's answer for sigma, I guess. But what is the value for the sigma for one of the planes, one side of the plane? Okay, I'll change it as sigma one side of the plane. Surface charge density for only one side of the plane. I think we discussed this in our earlier classes. Okay, that was, yes, Bhargav. But what's the value? That was half of this, right? Sigma 1 will be q by 2 pi, sorry, q by 2 epsilon naught. Remember? Sorry, sorry. Sigma is q by 2a. It's not, it was not epsilon naught, it was sigma by 2a. Why can't I write here? I'll write here go. Sigma 1 is equal to q by 2 times of a. So this was my electric surface charge density on one side of the plane. Now, yes, correct, Madhavi, correct, Bhargav. So, Madhavi, please check that it's q by 2a, not 2 times of q by a. Okay. Now, let us consider the flux passing through these three cylinder, these three surfaces of the cylinder as phi 1, phi 2, and phi 3. Let phi 1 be the flux because of the curved surface. And if you can see, phi 2 and phi 3 be the curved, flux through the plane surface. Okay. Now, if we try to calculate application of, if we try to apply Gauss's law, so we'll again consider this. Now, if we'll try to rotate this and align this, so we'll get the plane surface such that how can we see the plane surface, guys? If we try to align perpendicular or if we try to align it in this way, say we could see it like a thin line, right? If we have a plane surface, if you take a sheet of paper and try to align it, if you try to look its cross section side, only the side section side. If you try to see the side view, okay, I can say this. If you try to see the side view of the plane, how does it look? It looks something similar to this, right? Now, if I apply the same thing to this, so I have one surface area A with length D. I have another surface area behind this plane surface of area A and length D. We have maintained the symmetry, and we have the flux phi 1, phi 2, and phi 3, respectively, the fluxes for curved side and plane sides of the cylindrical surfaces which we have considered. So if we consider the electric field are emerging out. Okay, the electric fields are emerging out from the from the planar surface in both the directions, right? Let E be the uniform electric field emerging out. Then the flux passing through, the net flux. So if you want to calculate the net flux, what should we do? We have to add all these three fluxes, phi 1, phi 2, and phi 3. When we try to add them, what we get? So guys, what do you think the flux due to this curved surface be? Will there be any flux due to this curved surface phi 1? Will there be any flux due to this curved surface phi 1, guys? Please reply. YouTubers, Zoom people, please reply. No, why not? So if your answer is no, why? Correct answer. Cool. Others, please try to respond. So I received some messages. Yes. Yes. Correct. Ramakrishna Reddy. Correct. Hari Prasad. Correct. Bhargav. So why there is no electric field due to this? I mean, why there is no flux due to this? Because there is no electric field in this direction at all. There is no electric field on the curved surface at all, right? So the flux, I mean, the contribution of flux due to phi1 will be 0. Okay, but what will be the flux due to phi2 and phi3? So here the equipotential surface, the electric field is along the equipotential surface, and hence there is no electric field due to phi1, but there will be electric field due to phi2 and phi3, whose magnitude is given as, now if we want to calculate its magnitude, how can we find? So can we apply Gauss's law in these two surfaces for this phi2 and phi3? Can we apply Gauss's law to find the electric flux? Come on guys, reply, tell me. Yes, we can apply Gauss's law, right? So how can we apply? What is the expression we get? Tell me in general, what is my expression for phi? Phi equals to? Yes. Correct, Bhargav. Madhavi, check that. Check your answer. Hari Prasad, Ramakrishna Reddy, and Bhargav, correct answer. Others, guys, please try to answer. What is my flux now? What is my flux now? Phi. Phi2 and phi3 for these planar surfaces. Reply, guys, come on. I need a reply. Hello, guys, please try to reply. Yes, phi is equals to, how can we write? Q by epsilon, right? So we know the general expression, phi is equals to Q enclosed by epsilon naught. So what can we tell about Q in this condition, guys? Tell me what is Q from here for surface charge density. What will be my value of Q? Say if I say small q, what will be the value of Q for the surface charge density? Guys, come on, reply. Q enclosed or Q will be equals to. So how can I write my Q in terms of surface charge density and electric field? Okay, correct, Madhavi. Good. Yes, electric field times of my surface charge density. But guys, here we have the surface charge density already. How can we write? So we know sigma is equals to Q by A, right? Then what is Q from here? What is Q from here? Please respond, guys. Please respond. Respond, Marty. So Q will be equals to sigma times of A, right? Q will be equals to sigma times of A. Then what can I write my flux as? Okay, let me try to write the general expression for flux. For Gauss's law, we get phi is equals to integral, closed integral of E dot dA, that is Q enclosed by epsilon naught. Now my Q will be equals to, so the electric field due to the flux phi1, phi2 and phi3, sorry, phi2 and phi3 is given as phi2 plus phi3 is equal to integral E dot dA, that is Q enclosed by epsilon naught. But we know that Q enclosed is equals to sigma times of A. So we know sigma is equals to Q by A. From here we got this Q enclosed is equals to sigma times of A. Yes, correct, Krishmudi, correct, Lakshmi, cool. So others, please try to respond. Then can we write this phi2 plus phi3 will be equals to sigma times of A by epsilon naught. Can we write this? Click on yes or no. Can we write this? Guys, please help me derive. Please help me derive. So can we write this phi2 plus phi3 is equal to sigma A by epsilon naught? Yes, no. What happened, Hari Prasad? See, if anyone is not following, please listen again. So the electric flux due to phi1 was 0. Why? Because there is no electric field in this direction. But the electric field due to the planar surface was in both the direction, if you remember. What was the electric field? It was E, right? So we considered a small cylindrical surface of the equipotential surface to calculate the electric field for this condition, because we had already calculated the electric field using cylinders. So this will make our maths easier. So what did we do? We considered electric field in this direction and this direction only. There was no electric field here, so my phi1 was equals to 0. But yes, my phi2 and phi3 was not equal to 0, but my phi2 and phi3 are both equal of equal magnitude. What is my phi2, guys? Phi2 will be alone. Phi2 alone will be sigma times A by 2 epsilon. Okay. Why? Does anyone answer? Why is my phi2 is equal to sigma A by 2 epsilon, and why is my phi3 is equal to sigma A by 2 epsilon? Can someone answer this? ಹೇಳ್ತೀರಾ? Try ಮಾಡಿ. And let me know if I'm going faster. I don't know. Yes, correct. Yes, I represent. Correct, Madhavi. Madhavi Kumprapu gave me the right answer. I am from YouTube. Others, guys, here, Zoom audience, please respond. Yes, Prajwal. Yes. So my electric field, or yep, correct. Electric field on one surface area is sigma A by 2 epsilon naught. So electric field times of A, right? So this becomes my E. So this is nothing but my E. Can I write this? Okay. So yep. So my phi2 plus phi3. Okay. My phi2 plus phi3. If I add, I'll get sigma by epsilon naught. So no one should ask why didn't I write 2 here. So it's summation of, it's again I'll write here sigma A by 2 epsilon naught plus sigma A by 2 epsilon naught. Okay, so it's half of my electric field times of area. See, my surface area remains same, but my electric field will be sigma by 2 epsilon naught, because my surface charge density was given that way. Then yes, then if I try to solve, what would I get? So since my since symmetry, I get the value of sigma 2 and sigma 3 as E dot A. Then from here we can write that my electric field as EA plus EA is equal to sigma A by 2 sigma A by epsilon naught. Then if I try to simplify, 2EA is equal to sigma A by epsilon naught. From here I get electric field E is equal to sigma by 2 epsilon naught. So this was the expression which we were trying to derive for the electric field due to one side of the planar surface. Guys, please remember this is only for one side of the planar surface. So electric field is nothing but sigma by 2 epsilon naught. So yes, please remember this expression. Again, if anyone have any doubts in these steps, please let me know. So we had two planar surfaces. We considered there the cylindrical surface E with the electric field E of length D. Then when we try to calculate the flux phi2 and phi3, phi2 plus phi3 equals sigma A by epsilon naught. So since they are of the symmetry, phi2 will be equals to phi3. When I try to add them, then we'll get phi2 is equals to phi3 is equals to E dot A. That is 2 times of E dot A is equal to sigma A by epsilon naught. If you try to simplify and find the value of E, I'll get sigma by epsilon naught, sigma by 2 epsilon naught. Electric field E is equal to sigma by 2 epsilon naught. My A and A cancels here, and whatever remaining is E is equal to sigma by 2 epsilon naught. This is for one side of the plane surface only. Okay. Any doubts in this, guys? Please let me know. Any doubts in this? Hope you guys have understood. Guys, please reply. Yes, yes, Hari Prasad. So what will be for two sides, guys? If I want to find my electric field for a combination of two sides, say for one side I have sigma by 2 epsilon naught. If I consider the electric field due to both the sides, what will be the value? Everyone please try to answer. If I want to consider the electric field due to both, again I have to go in the reverse direction then. What will be my flux, net flux, phi? Or what will be my net electric field if I try to combine these two? What will be my E? So for one side of the plane, we have E is equals to sigma by 2 epsilon naught. For two sides of the plane, if we combine, if I want to find my E net, what will be it? What will be the magnitude of E net? Or can I put this way? What will be the electric field at the midpoint? Are you sure, guys? Say, okay, I hope you guys took it in this way. Say if I have two electric, okay, so this we'll be studying again in our capacitors problem. Say if we have two conductors, say if we have two infinite plane, if you have two infinite plane, the charge will be only on one side. Say if I say the electric field distribution is only on one side, over here on this surface, and over the inner surface of this. Okay, then what can be the value of electric field E? No, Manoj. Okay. So in this case, guys, it will be sigma by epsilon naught. Okay, because this will be sigma by 2 epsilon naught. This will be sigma by 2 epsilon naught. So summation of these two will be 2 sigma by 2 epsilon naught. So from here, I'll get 2 cancelled. But at the midpoint, see, electric field is along this direction for this. I mean, at the midpoint of this, what will be the electric field? Will there be any electric field at the midpoint of this plane? Suppose if I want to calculate the at the midpoint, if I want to calculate electric field, what would be the net electric field at the midpoint or any point on the equatorial plane? Guys, इस्ट बेगा मरतोद रहेंगे. See, my electric field at the midpoint for this planar surface would be, okay, tell me this. Say my electric field is plus E, say 10 volts per meter in this direction, again 10 volts per meter in this direction. So if I want to give directions, vectors, so I'll call this plus 10, I'll call this minus 10. So what is the net electric field in the midpoint? Correct, Ramakrishna Reddy. At midpoint, my electric field, net electric field will be 0. If you remember, we use the same thing for dipole also. Say if we had a dipole and there was at the midpoint, we got an equipotential surface whose magnitude was 0. At midpoint, it will be obviously 0 because see electric field in this direction, it's plus E cap, plus E with the direction of I cap. Here plus E in the direction of minus I cap, right? E net will be 0 at the midpoint. But suppose if we have two such planes, see, that's what we are going to study in the capacitors again, guys. I'm repeating this again, stressing this again. If we have two plates, each with surface charge density sigma, then the electric field for one of the plate will be given as sigma by 2 epsilon naught. For the other plate, it will be sigma by 2 epsilon naught. The electric field originated from between these two will be having a magnitude of E is equal to sigma by epsilon naught. Artha aita? Understood, guys? Guys, please respond. Hello. So Okay, cool. So hope you guys have understood this. This was the expression for electric field due to an infinite plane conductor. Okay, cool. Yes. So I'm giving you a problem. If you have learned this, please try to find this answer. Any doubts, guys? Please let me know before I go to the problem. Let me know if you have any doubts. Okay, Ramakrishna. Thank you, Ramakrishna, Reddy, for confirmation. Thank you, Krish Modi. Here, guys, please let me know if you have any doubts. ಯಾರಿಗಾದ್ರೆ ಏನೋ ಡೌಟ್ ಇದ್ರೆ ಕೇಳಿ ಅರ್ಥ ಆಗಿದೆ ಅಂದ್ರೆ ಅರ್ಥ ಆಗಿದೆ ಅಂತ ಹೇಳಿ, so that I can move on. Guys, come on. Okay, at least click on yes if you have understood this. If you have any doubts, click on no. Come on, guys, please answer. Yes. Okay, cool. Thank you, guys. Okay, then if you have understood, let's try to solve some questions. So I have a question for everyone here. So the question goes like this: say I have a uniform electric field. They have launched a poll. Say consider a uniform electric field of E is equals to 3 into 10 power 3 I cap newtons per coulomb. So this electric field is in this direction. Okay, I plus I cap direction. So its value of is E is equals to 3 into 10 power 3 newtons per coulomb. Now, what is the flux of this field through a square of 10 centimeter by 10 centimeter? Say what's given in the question. I have okay, cool, Manju, cool. Say I have 10 centimeter by 10 centimeter square conductor. Say I have a square conductor whose plane is parallel to the YZ plane. So I have so X, Y, and Z. So it's parallel to the YZ plane. So it's along the X plane. Okay. Simply, if it's parallel to the YZ plane, it's along the X plane. I mean X axis. So my X axis is here. My YZ plane is this. So what is the flux? Calculate the flux through this surface. Come on, guys. Okay. Hari Prasad and Manju had given me the answer in chat box, and only one have given me the answer in the poll. Guys, come on, try to answer this, please. Everyone, please try to answer. Okay, Prajwal. Also answer in the polls. Zoom audience, please answer in the polls. Cool, correct. So first answer. Guys, please check everyone. Please check your answers. Always check your answers. Yep. So most of you, Bhargav correct, Ramakrishna Reddy correct, Krish Modi correct, Hari Prasad correct. Here, who else had given me? So there were many people who had given me the answer. Say here in Zoom, I got Anusha, Manju correct, Prajwal correct, Rakesh correct. Just please try to answer. Answer Madi, guys. Yes. Most of you have given me the right answer. So waiting for more responses, guys, please. So I have received 10 responses nearly out of 20 students. Why? What happened to other 10 students? Okay, I'm going to end the poll. So we'll check the answer. Okay. So yes, all of you had given me the right answer. The answer is B. So we'll check how it comes. Okay. So yep. So what is the flux formula, guys? Phi is equals to E dot A. So what is my area? Area is 10 into 10. That is 10 into 10 into 10 power minus 4 meters. Right. So this will be 10 power minus 2. So phi is equals to, what is my E? 3 into 10 power 3 into 10 power minus 2. So this will be 30 Newton meter square per coulomb. So option B is the right answer, guys. Come on. Awesome, guys. Superb. Correct. So then try to answer this question. So I have another question for you guys. So again, what is the flux through the same square? Say if I have the same square, if the normal makes an angle theta of theta equals to 60 degree with the x-axis, what will be my answer? What will be my flux in this case? So in my previous case, I had it was my theta was, what was my theta value in previous case, guys? It was 0 degree. Here, what will be my answer? Okay, cool. Okay, so I launch the poll. Zoom audience, please try to answer in the poll. Yes, correct, Tejas. Awesome. Super. Guys, please, some people are trying to answer without noticing it. Correct, Manju? Krish Modi, correct. Rama Krishna Reddy, correct. Yes, Hari Prasad, we have to convert to meters. Correct, Hari Prasad. Rakesh, correct. So some people had also given me the wrong answer in Zoom. Please note check them. So those who gave me the wrong answer, please notify or please correct that. Anusha, correct? Come on, guys, come on. Reply. Okay. Again, I received 10 responses. Other 10, please try to respond. Okay, so I'm going to end the poll. So, yep, 2 of them had given me the wrong answer, but 6 of them had given me the right answer. So correct answer is option A. So how to solve here, guys? Come on. My flux will be phi is equals to E dot A, that is EA cos theta, right? So just substitute the value of cos theta, that is 3 into 10 power 3 into 10 power minus 2 into cos theta is cos 60, 1 by 2. So that will be 15 Newton meter square per coulomb. So option A is the right answer. Yes, guys. So we, yep, understood. I hope this was simple question. So I have one more question to you guys. Come on, try to solve this. Hope you guys have understood this question. Any doubts in this? Okay, no doubts. Cool. So please try to answer this question now. Take some time to check. Sorry. Take some time to check and try to solve this question. So this was a JEE mains question, guys, from your previous. It was one of your previous year question. Please try to answer this. So a charge Q is placed at a perpendicular distance. So similar question was asked in your day mains. So answer is very simple for this, but if you try to know, if you try to apply the concepts which you have learned, answer is very simple. So what's given here is a charge Q is placed at a perpendicular distance A by 2 above the center of a horizontal square surface of edge A. So one side length is A, shown in the figure. Find the flux of the electric field through the square surface. Guys, I want every one of you to answer this question. Please try to answer. Okay, Bhargav had already answered. Bhargav, right answer. Ramakrishna Reddy, correct answer. Hari Prasad, check your answer, please. Correct, guys. Come on. People at Zoom, please try to respond. Okay, so I have received. So many of you have voted. Cool. Out of these 16, okay, 6 responses have only one correct answer. They just please check the answer again. Check your answer. So guys, the principle which we use here is Gauss's law. Again, which we studied a few moments ago. It's about the electric field through a plane surface. Please go through that. So guys, there is only one simple trick. If you get to know this, you'll get the answer very easily. So what were the two conditions for application of Gauss law? What were the two conditions for application of Gauss's law? So if you know that, your answer is ready. Okay, guys. So others, please try to respond. I am not getting any response. So I'll give you a hint, guys. Is this okay? I'm trying to give you yes, Manju. I'm correct. So, guys, is this a symmetric surface? So, for application of Gauss's law, the two conditions should be satisfied. First condition was my electric field should be uniform and parallel to dA, right? Again, my dA should be symmetric. So how to find, is it in symmetric? Is my given surface, whatever the square which they had given, is this surface symmetric with respect to the charge? Yes, correct, Bhargav, exactly. Yeah, that's the trick which we have to check here, Bhargav. Yes, Namrata, correct answer. So guys, for can we achieve symmetric here, symmetric condition here for this square? So how can we achieve symmetric condition in this case? Come on, guys, tell me. So I want Zoom audience also to respond, please. Students at Zoom, please respond. Only students in YouTube are answering so far, and I request you guys also. I mean, yes, there are people answering. Please answer the way how to approach this problem. So I want you guys to figure out how to approach this problem. Come on, guys. There are. It's a very simple thing. So how can just tell me? Hello, guys. Please just tell me one thing. How can I consider the symmetry in this case? So I received one answer already. So that was right. So how can we achieve symmetry? How to achieve symmetry? So if we try to start with integration and application of Gauss's law, the way with the math, it gets complicated. Okay. So in this case, what we do, what's given here, we are given with a plane surface of side length A from the center at a height of A by 2. At a height of say A by 2, I have a charge. I have a charge Q placed. Now, guys, how can I achieve my symmetry? How can I achieve this symmetry? So to achieve symmetry, can I draw an imaginary cube? So can we draw an imaginary cube? With a distance A by 2. So let's consider. So let us consider a small cube of length A. Say this side length of one side of the face of cube is A. How many faces does this cube have? Yes, correct, Bhargav. So if the face has 1, 2, 3, 4, 5, and 6 faces, right? My cube has 6 faces. So if the net flux if the net, yes, correct, Tejas, correct answer. So if the flux through this charge, so if I try to draw the electric field because of this charge, my electric field will be in all directions, right? So it will be in all directions. The total flux phi will be given as phi is equals to Q enclosed by epsilon naught from Gauss's law. So if this is Q enclosed by epsilon naught from Gauss law, what is the value of flux due to only one of the phase? Yes. What is the value of my flux due to one of the phases? Only one of the phases. Answer this, please. What is my flux if my charge is emitting electric field in all 6 directions, 6 faces of cube? Then what will be? Yes, it will be 1 by 6 times of total flux through one plane surface. One surface is 1 by 6 times of total flux, that is Q enclosed by 6 times of epsilon naught. This will be our answer. Okay, so option C is the correct answer. Okay, so this question was asked in your day mains, guys. Please understand. If you have any doubts, please ask me. Okay, cool. Yes, awesome, guys. So hope you guys have understood this. Any doubts in this? Any doubts in this? So I'm waiting if you have any doubts. Okay, so we have come to, yes, correct. Sir, if it's a cylinder, then okay. For cylinder condition, we have a different case, Hari Prasad. So we had tried the expression for cylinder. Flux was nothing but, so if you remember, for cylinder, it was the surface, only through the curved surface we got that flux. So phi 1, then we had tried to find the electric field by applying Gauss's law. Phi is equal to Q enclosed by surface area, that is 2 pi RL. If you remember, Q enclosed by 2 pi RL. We had used this expression for finding a cylinder. So cylinder case is different from this. So if we had a regular surface, we can try to apply. Hari Prasad. Okay, any other doubts, guys? Any other doubts? Okay. So we have completed this chapter, electrostatics. So let's have a quick summary. So we started with electrostatics, which means electric charges. So we'll have a quick summary. Guys, please help me to summarize this. So electrostatics is it made of 2 words, the electric charges which are at rest. So this was the first definition which we started with electrostatics. Which we started the electrostatics with. So electrostatics and electric charges which are at rest. Study of electric charges which are at rest is electrostatics. Then we checked with the charge. What is a charge? So charge can be either the abundance or absence, or say if I have more electrons or if I have less electrons. It's either the abundance of electrons or it's the deficiency. Abundance or deficiency of electrons in a charge, in a body, in a neutral body. In neutral body gives me rise to charge, right? So charged ion or charged ions, I should say charged ion. For charged ion, I should have an abundance of electrons or deficiency of electrons. Say if I have abundance of electrons in a neutral body, what would I get? Tell me, guys. If I had an abundance of electrons, what would I get? I would get a negative charge. If I have deficiency of electrons, I would get a positive charge. Next, we learned about Yes, properties of charge. So what were the three properties of charge we learned? So then we started with properties of charge. So first property was like charges. We'll discuss that, Hari Prasad. So let me complete this. So properties of charge say like charges repel, unlike charges attract. Right? Then come on guys, tell me what was the second property? Second property ಹೇಳಿ ಏನಿತ್ತು? Hari Prasad will discuss in the end. Okay. So what was the second property, guys? Come on, tell me. Hello. Rappa. So we had the second property as quantization of charge. So charge, whenever we transfer a charge, it's always Q is equals to n times of E plus or minus NE. It's always transferred as a multiple of an integer. Then the third property we had conservation of charge, right? Charge can neither be created nor be destroyed, but can be transferred from one form to other, from one body to other body. So next we try to check with modes of charge transfer. What are the modes of charge transfer, guys? Please help me complete this. What are the modes of charge transfer? Then we started modes of charge transfer, right? So first mode of charge transfer was conduction. So in conduction, we had two conditions. There should be a potential difference and there should exist touch. So there should exist a potential difference and there should, the two bodies should touch. These were the conditions. Then same type of charge, same charges will flow. Same type of charge will flow from conducting body to charge, from charge body to conducting body. Then we had, yes, friction, correct, Manju. So in friction, when we rub two non-metals or a metal with a non-metal also would give me, when we rub two non-metals or two bodies, I'll say two bodies. So one would get positively charged, one would get negatively charged, right? Then third condition was induction. Say induction. What is induction, guys? Induction, the forced charge. So when I bring a negatively charged body or when I bring a charged body near a uncharged body, there is formation of net positive charge on the net opposite charge. Say net opposite charge is on other body. So this is always attractive. Induction is always attractive in nature. Okay, so these were the three modes of charge transfer. Then we started with Coulomb's law. So what was Coulomb's law? See, entire electrostatic chapters is only on this law, Coulomb's law. So the Coulomb's law gave expression for what? Force experienced, force between 2 point charges. So Coulomb's law is applicable only for point charges. So it is given as F is equals to K times of Q1 Q2 divided by R square, where K is nothing but 1 by 4 pi epsilon naught. What is epsilon naught, guys? Correct, Chinmay. Thank you, Prajwal. So what is epsilon naught, or epsilon in general? What is epsilon? Epsilon means permittivity, right? So what is permittivity? How much a body opposes the free flow of charge. Okay, permittivity is how much a body opposes free flow of charge through it. Then epsilon value is 8.854 into 10 power minus 12 coulombs meter square per Newton. Okay, coulomb meter square per Newton. Next, it was, yes, correct, guys. Next, what did we learn? We learned electric field. We started with something called as electric field. After Newton's, after Coulomb's law, we started with electric field. So what happened in electric field, guys? What is an electric field? So this electric field concept was given by whom? If you guys remember, who gave the concept of electric field? There exists an imaginary field, electric field. So hope you guys remember. So this was given by Michael Faraday. Again, the concept of electric field, where he tried to explain that two charges try to talk. Say if there exists a positive charge and a negative charge, they try to communicate each other. Say, okay, sorry. They try to communicate each other with the help of electric field lines. Say again, so we started with electric field. So we started with rules to draw electric field lines. What were the rules? First rule, my electric field lines start from positive and at negative, right? And at negative charge. So note 2, again guys, come on, tell me, what was the second rule? What was the second rule for electric field lines? What was the second rule for electric field lines? No two electric field lines cross each other, right? Next, third rule, my electric field lines are continuous. Is it continuous? Continuous in a charge free region, right? Again guys, last rule, what was the last rule? It would not never form what? Electric field lines will never form what? Yes, we had completed the intersection part, Lakshmi. So the electric field lines never cross each other. Yes, correct, Prajwal. Electric field lines never form closed loops. Yes, correct, Ganesh. So electric field lines will never form closed loops. So then what is the expression for electric field, guys? Electric field is given as E is equals to, yes, correct, Hari Prasad, correct, Lakshmi. Heli, electric field E is equals to, yes, K times Q by R square or F by Q. E is equals to F by Q, that is K times of Q by R square. And yeah, again in Coulomb's law or in electric field, what is the direction of my force? What is the direction of force? Direction is along, come on guys, tell me, what is the direction of electric field lines for electric, sorry, for case of force, for force, what is the direction of electric, what is the direction of force acting between 2 point charges? Force direction is along, yes, line joining 2 points, correct, point charges, okay. So force, for force line direction was along the line joining 2 points. Then for electric field direction, yes, joining the 2 points and below, yes, correct, and always acts between the center, yes, right. So my electric field direction is given by what? Say if I have a charge, say positive charge, then how can I write my electric field lines direction? How can I give my electric field line direction? What should I draw to this electric field line to get the direction? What should I draw to get the electric field line direction? Guys, don't forget, we should try to draw a tangent. Yes, tangent drawn to electric field lines. Then, how can we find the strength? So electric field lines also talk about strength. How? How does electric field lines talk about strength? Really? Yes, correct, Bhargav. But it's a tangent drawn to the electric field lines gives the direction. Okay. So how does electric field line talk about strength? Hinge ಹೇಳುತ್ತೆ strength. How would it predict the strength of the electric field lines? So two things. One is density of electric field lines. Second is gap between two consecutive lines. So if gap is less, if gap is less, electric field line strength is more. Hoda, if my gap is less, electric field line strength is more. Okay, so this was much of electric field lines. Then we try to calculate the electric field, right? So what we study in electric field? So we have given the expression. Say if we have system of charges, say if I have many charges instead of only two charges, if I had many charges, how did I find my electric field and force? So we'll try to find system of charges here. First, let's talk about force. What did we do for n number of charges? If you remember Q1, Q2, and Q3 acting on this small test charge Q. So what was considered here? So F net is nothing but summation of, it's the summation of F12 plus F1Q, F2Q plus F3Q. If you remember, similarly for electric field also, E net. So if I had E net was equals to E1 plus E2 plus E3. Okay, so these were much of it which we learned for the electric field and force. Then we started with, so we had completed this electric field and stuff. Then we started with what? Next time start madadvi. We started with the different conditions. Which was that? Which were the two different conditions which did not satisfy quantization of charge? Yes, vector addition. So this was vector addition. Okay, before we go there, what was potential? Okay, we started with potential, electric potential. So the amount of work done, say we had 2 point charges which were separated by a distance r. Now these two were positive charges. One felt unhappy and it went far away. So this both were positive charges. So I had to do some external work to bring this back. So what was that work external? External work done was given by W external is equals to. Come on, guys, tell me. It was nothing but minus of Fe times of the distance d. So this, when we simplified, we got that as W external is equals to K times of Q by R, K times of Q into 1 by R1 minus 1 by R2. So guys, this was the expression for electric field, sorry, net external work done. Say if this is conservative, if this force applied was conservative, what can we write this W external as? Guys, please try to respond. Please help me. So what is my W external if I had the force as conservative? This can be written as change in potential energy. Okay. Then, so we started with electric potential. It's nothing but the change in potential energy per unit charge was my potential. So next we try to check for the conditions of dipoles and continuous charge distribution. So for a case of dipoles, okay, I have last page here. So for the case of dipole, electric field was given as E is equals to 1 K times of 2P by R cube for the condition, which condition? Axial condition, axis. For electric field along the perpendicular bisector, we had E is equals to P by 4 pi epsilon naught into 2R by R square minus A square whole power 3 by 2. So this was, okay, I'll write equatorial point. So without neglecting A for this, we had for axis, it's P. Come on guys, please respond. It's P by 4 pi epsilon naught into 2R by R square minus A square whole power 2. So this was a general expression for axial condition. This was the general expression for equatorial conditions. Then we try to find the electric flux. Okay. So we try to find the potential with this. We derived an expression E dot dr. E dot dr is equals to minus dB, or E dr cos theta is equals to dV minus dV, or V is equals to minus E dot r. So these were the three expressions which we derived, relation between electric field and potential. Then also we try to calculate what? The flux. After these we try to come to Gauss law. So before Gauss law we try to check flux. Phi is equals to E dot A. Then we derive the area vector. A is equals to magnitude of A, and n cap will be the normal. Normal direction would be the direction of my electric field, or area direction of area vector. Then we try to apply Gauss law. Gauss law ಏನito? For flux, we try to find the expression that is Q enclosed upon epsilon naught. So using this, we try to check for the sphere and infinite rod and plane, infinite plane condition. So for sphere, we got the formula as, so we try to find the electric field due to the sphere, that is given as E is equals to 2 lambda by 4 pi epsilon naught r. Similarly for infinite plane, infinite rod, we got E is equals to sigma, sorry, E is equals to, so this was for infinite rod, right? For sphere, we had a condition. For sphere, we had surface charge density. So that is C is equal to sigma by 2 pi epsilon naught times, yes, to the sphere. Guys, tell me what was for sphere here? Okay, we missed the torque condition. Okay, so in dipoles, we had two dipoles present in the electric field, uniform electric field. It experiences a torque that was given by dipole torque. Yes, correct guys. So for dipoles, whatever the torque, tau is equals to Pe sine theta, if I'm not wrong. So tau is equals to P cross E was present there. Again, Then yeah, coming to Gauss law, we studied about sphere, about the linear conductor and plane, which we studied today. Okay, we'll check that. So please check that all those conditions, and also please check in your page 8 of your page 7 or 8. I think it's page 7 and 8 of module. You have all the expressions for Gauss law, for sphere, infinite rod, and plane. Also, there is given some graphs. Please go through them. Okay. So this is much of it, guys. This was your electrostatics. Cool. So we have completed electrostatics. So from tomorrow onwards, we'll be starting with capacitance and capacitance of capacitors. Okay. We'll start with capacitance and capacitors from tomorrow. Please come with the preparation. Okay. So I want you guys to prepare with Gauss's law and also the expression for electric field due to Gauss's law. I mean, application of Gauss law for the infinite electric field, infinite plane condition. And also please try to revise electric field and electric potential concepts. Okay. So it will be helpful for us to discuss about capacitors in tomorrow's class. Okay, guys. Cool. Thank you, guys. So this is one of the lengthiest chapter, one of the lengthiest. So next we have three such chapters. Okay. So one is electrostatics. The second lengthiest chapter is your current electricity. So again, so that's very important, and at the same time it's very simple yet confusing, a bit confusing. Next we have one similar lengthy chapter is ray optics. So these three chapters are very important. These three fetch very high marks, or these stands as a basic. Please go through this, and I'll also share some additional questions. So I had shared few questions as your DPP. So some students had also tried to contact me in last 2-3 days. And, I don't know, I was not able to respond because of various conditions. Please, if I have not responded yet, let me know once. Anyway, I'll try to respond. I have responded for 2-3 students via WhatsApp. So if anyone had any doubts in any of those questions, please try to approach in the WhatsApp. Okay. Yes, those three chapters are very important, 100%. So guys, please try to give the feedback, and we'll start with the next chapter in next class. So yes, our next class is on Thursday, right? We'll start with that. And guys, you will be having test this weekend. There will be test on this chapter this weekend. Okay. So I'll make a note of that. Test for electrostatics. What's the date, guys? Does anyone have any idea about date? What's the day on Sunday? Date of Sunday? Okay, it's 22nd if I'm not wrong. 2nd November 2020. Cool. So if you have any doubts on this particular subject, I mean on this particular chapter, we'll be having a doubt session on Friday. Okay, we'll be having a half class. Say, I'm thinking to conduct a doubt session. So all doubts you have, you could post it in your group or post it in the WhatsApp. okay, in your WhatsApp group, or post it in your Telegram group, or send me to my number. Okay, that way I can come prepared to your doubts. So you could contact me with this number. So you can send all your doubts here. So if I have not yet discussed your doubts yet in your Telegram or your WhatsApp, we'll discuss that on Fridays, half class. Okay, half class will complete the capacitors chapter, and the other half will discuss the doubts. Okay, cool guys. Then come prepared with capacitors for next class. So we have completed capacitors. Congrats. And yes, we'll meet again in our next class. Okay guys, thank you. Then see you all. Hope you enjoyed your vacations very much. Okay guys, see you then. Bye bye.